Welcome to the Hydrogen Studies podcast. Today we're diving into a common but often misunderstood condition, kidney stones. They're painful, they're stubborn, and once you've had one, there's a high chance they'll come back. But what if a tiny molecule like hydrogen could help us understand and maybe even influence how kidney stones form? Let's get into it. This is the Hydrogen Studies podcast, sponsored by Echo Water. Kidney stones form when substances in the urine, like calcium, oxalate, phosphate, or uric acid, crystallize and stick together. While that may sound simple, the actual biology is anything but. In a 2024 review, Tamburino and colleagues laid out the multi-step process behind stone formation and recurrence. The key idea: stones don't just happen because there's too much of something. They form because the urinary environment becomes favorable for crystallization, adhesion, and growth. It begins with supersaturation, where the concentration of certain solutes in the urine exceeds the threshold for crystal formation. In most people, these crystals get flushed out before they can do any harm, but if the conditions are right or wrong, they can stick to the walls of the renal tubules and start building. What makes those conditions right for stone formation? Tamburino's team identified several contributing factors. Urinary pH plays a central role. Some types of stones, like calcium oxalate or uric acid, form more easily in acidic environments. Others, like calcium phosphate, thrive in alkaline urine. Even small shifts in pH can tip the balance towards stone formation. 2. Deficiency of crystallization inhibitors, especially citrate, is another major factor. Citrate binds to calcium and prevents it from combining with oxalate or phosphate. Low urinary citric levels, common in people with metabolic syndrome, low fluid intake, or high-protein diets, remove this natural safeguard, making stones more likely to form and grow. 3. Oxidative stress and inflammation are emerging as key players in both the initiation and progression of stone formation. Damaged epithelial cells and renal tubules, often injured by oxidative stress, can act as adhesion sites for calcium crystals. These cells express molecules that promote crystal attachment and retention, essentially turning the kidney's surface into a sticky landing pad for new stones. 4. Chronic or repeated inflammation may also disrupt normal urine composition by altering protein excretion, acid-base balance, and immune signaling. Tamburino emphasized that inflammation is no longer seen as a consequence of stones, it's part of their cause. And finally, Randle's plaques. Calcium phosphate deposits beneath the kidney's inner lining serve as nucleation sites for stones. These plaques can break through the epithelium and act as scaffolds for calcium oxalate to accumulate, especially when urinary conditions favor aggregation. This complexity is why kidney stones are so difficult to manage long-term. You're not just trying to reduce calcium or oxalate levels. You're working against a multi-layered process involving chemistry, cell biology, and chronic stress signals inside the kidneys. So while we often think of kidney stones as a mechanical problem, something getting stuck, the truth is that they reflect a broader metabolic and inflammatory imbalance. And understanding this has changed how scientists approach both treatment and prevention. It's no longer just about increasing water intake or cutting back on spinach. It's about supporting the kidney's ability to maintain a stable internal environment, one that resists crystal formation, clears waste efficiently, and protects itself from cellular damage. When we think about kidney stones, we often picture hard crystals causing sharp pain. But before those stones form, before they grow large enough to block a ureter, there's something else going on behind the scenes: oxidative stress. A 2024 review by Chen and colleagues, published in the World Journal of Urology, took a closer look at this connection. The researchers examined how oxidative balance, the body's internal tug-of-war between antioxidants and free radicals, relates to kidney stone formation in adults. They used a tool called the Oxidative Balance Score, or OBS, which combines information about a person's diet, lifestyle, and metabolic profile. It weighs factors that increase oxidative stress, like smoking, inflammation, or poor nutrition, against those that counteract it, such as antioxidant-rich foods and physical activity. The results were clear. A lower OBS, meaning more oxidative stress and fewer protective factors, was strongly associated with kidney stones. In other words, people whose bodies were under more oxidative pressure were more likely to develop stones. This is significant because it reinforces the idea that kidney stones aren't just about what's in your urine. They're about what's happening at the cellular level inside your kidneys. Oxidative stress damages the cells that line the renal tubules. When these cells are inflamed or injured, they can no longer repel crystals effectively. Instead, they start expressing adhesion molecules, essentially sending out signals that invite crystals to stick. Chen's findings also help explain why some people get recurring stones, even when they're following all the typical advice: drinking water, limiting salt, reducing oxalate. If their bodies are in a state of chronic oxidative imbalance, their kidneys may stay in a pro-stone environment, regardless of what's happening in their diet alone. This perspective shifts the way we think about prevention. It's not just about lowering stone-forming compounds. It's also about improving the kidney's resilience to stress, its ability to defend against damage, maintain a non-adhesive surface, and repair itself when injury happens. That's where the idea of using antioxidants or anti-inflammatory strategies becomes more interesting, and it's where molecular hydrogen enters the conversation, not as a cure, but as a possible way to support the kidney's natural defenses against oxidative damage. Because, as Chen's analysis shows, oxidative stress isn't just present in stone formers. It may be one of the root conditions driving stone development in the first place. Let's have a quick word from our sponsor. Your body is a system, and when it's running right, you feel focused, energized, in flow. But sometimes we struggle to find that flow state. Why? Because there's too much static in our system: brain fog, fatigue, and inflammation. The Echo Flask clears the static by infusing your water with molecular hydrogen, a natural, science-backed gas that helps your body think sharper, recover faster, and run smoother. This is more than hydration. It's better focus, more energy, faster recovery, less internal stress, and long-term benefits that keep you sharp. When your water works harder, your whole system does too. Find your flow state with the Echo Flask hydrogen water bottle and get an unlimited supply of hydrogen water at home and on the go. Visit echowater.com and use code H2Studies to get 10% off of your first order with Echo Hydrogen Water products. With human research still in its early stages, most of what we know about molecular hydrogen in kidney stones comes from animal studies. These give us a controlled way to explore how hydrogen might influence stone formation and kidney injury, especially through its effects on oxidative stress, inflammation, and tissue repair. Let's start with a 2015 study by Pang and colleagues. In this experiment, researchers used glyoxylate injections to induce calcium oxalate stone formation in mice, a widely accepted model for studying human kidney stones. The mice were then split into groups, with some receiving 67% hydrogen gas through inhalation. The results? Mice that inhaled hydrogen had significantly fewer calcium oxalate crystals in their kidneys, lower levels of malondialdehyde, MDA, a marker of oxidative damage, and healthier kidney tissue overall, with less cellular injury and inflammation. What's the takeaway? Hydrogen gas didn't prevent crystals from forming in the urine, but it did make the kidney tissue less reactive, less inflamed, and more resilient. That meant fewer crystals could attach and less damage occurred when they did. Fast forward to 2018, and a team led by Lou took a deeper look at how hydrogen might be working at the metabolic level. Using a similar mouse model, they again delivered hydrogen gas via inhalation, then ran UPLC-MS-based metabolomics, a technique that measures shifts in hundreds of metabolic pathways. And what they found was striking. Hydrogen-treated mice had altered levels of metabolites linked to amino acid metabolism, energy regulation, and oxidative stress pathways. These changes suggested that hydrogen wasn't just lowering ROS, it was supporting a broader restoration of kidney cellular function, especially in the context of inflammation and injury. Finally, in 2021, C and colleagues tested a different approach: oral hydrogen-rich water rather than inhaled gas. Again, using mice with calcium oxalate-induced kidney injury. They observed reduced oxidative stress and lipid peroxidation, lower expression of inflammatory cytokines, including TNF-A and IL-1B, and decreased fibrosis, the scarring that made kidney damage permanent. What made this study especially valuable is that hydrogen was delivered through drinking water, a much more practical route for long-term use. The results showed that even without directly interfering with crystal formation, hydrogen helped preserve kidney structure and function by suppressing the cascade of inflammation and scarring that follows. So across 3 studies with different delivery methods, different outcome measures, and different research teams, we see a consistent story. Hydrogen seems to help the kidney tolerate injury better. It doesn't stop the chemistry of stone formation outright, but it reduced the likelihood that crystals will cause lasting harm. It makes the tissue less reactive, less inflamed, and more stable under stress. And that's important because the real damage from kidney stones isn't always from the crystals themselves, it's from the body's reaction to them. If we can make the kidney a less welcoming environment for adhesion and inflammation, we might be able to reduce not just stone burden, but long-term kidney injury. These studies don't answer every question. They were done in mice, not humans, but they give us a compelling hypothesis that molecular hydrogen may not treat kidney stones directly, but it might support the underlying biological conditions that help the kidney resist injury and recover more effectively. So far, the research paints an encouraging picture. In mouse models of calcium oxalate kidney stones, molecular hydrogen, whether inhaled or delivered through drinking water, has been shown to reduce oxidative stress, inflammation, and tissue damage. It may even shift metabolic activity toward a more protective state. But before we run too far with these findings, let's be clear about what this research does not yet tell us. First, all of these studies from Pang in 2015 to Liu in 2018 to C in 2021 were conducted in rodents. Animal models are valuable tools, but they don't capture the full complexity of human kidney stone disease. Differences in diet, hydration, genetics, and even gut microbiome composition all influence how stones form in people, and these variables don't always map clearly onto laboratory animals. Second, the mice in these studies were intentionally overloaded with oxalate to rapidly induce stone formation. That's useful for testing mechanisms under stress, but it doesn't mirror the slow, often invisible progression of stone development in most humans. In people, stones typically form over weeks or months, and many are never noticed unless they grow large or cause obstruction. And third, while these studies clearly show biological effects, lower oxidative stress, reduced inflammation, less fibrosis, they don't establish long-term prevention or recurrence outcomes. In other words, even if hydrogen protects against tissue damage in the short term, we don't yet know whether it lowers a person's lifetime risk of forming new stones or improves kidney function in the long run. Finally, none of the studies explored optimal dosage, timing, or delivery route for hydrogen in a human clinical setting. In the lab, it's easy to control exposure to 67% hydrogen gas or highly concentrated hydrogen water, but translating those doses into a daily routine that works safely and effectively for people is a different challenge altogether. So what can we say with confidence? Hydrogen shows consistent protective effects in preclinical models of calcium oxalate kidney injury. It appears to buffer the biological environment, making the kidney more resistant to oxidative damage and less likely to develop inflammation or scarring in response to crystals. But we don't yet have clinical trials in humans with kidney stones, no randomized studies, no long-term follow-up, and no head-to-head comparisons with conventional therapies like citrate, thiazide diuretics, or dietary changes. This means hydrogen is not a treatment, not a substitute for medical advice, and not a cure. Still, these findings do raise a compelling possibility that in the future, molecular hydrogen could become part of a broader strategy, not to dissolve stones, but to support the body's resilience against the conditions that allow them to form and cause harm. That kind of support, targeting oxidative stress, stabilizing kidney tissue, and promoting recovery, could prove valuable, especially for people who struggle with recurring stones or have underlying metabolic vulnerabilities. But to get there, we'll need human studies, carefully designed, rigorously tested, and focused not just on stones, but on the full picture of kidney health. Kidney stones have long been seen as a problem of chemistry. Too much calcium, not enough fluid, too many oxalates in the diet, and that's still true, but the science is moving us towards a broader view. The 2024 review by Tamburino laid the foundation for this shift. It explained how stones don't just form because of what's in the urine, they form because of what's happening in the tissue, in the cells, and in the microenvironment of the kidneys. Oxidative stress, inflammation, pH shifts, crystal adhesion molecules, these are not secondary players. They're part of the root system. And as the 2024 review by Chen suggested, a person's overall oxidative balance may be one of the strongest predictors of stone risk. So where does this leave us? It leaves us with a new framework for prevention, one that goes beyond food lists and fluid intake and begins to ask, how resilient is the kidney's internal environment? How well can it defend itself from oxidative injury? What systems are in place to prevent crystals from turning into inflammation, fibrosis, and long-term damage? And that's where molecular hydrogen becomes more than a chemical curiosity. In every animal model reviewed, from Pang's inhalation study in 2015 to lose metabolic mapping in 2018, to seize oral hydrogen water experiment in 2021, hydrogen supported these exact processes, not by preventing oxalate from entering the body or dissolving crystals overnight, but by making kidney tissue less inflamed, less damaged, and less reactive. And that's a different kind of intervention. It's not blocking the problem, it's about helping the body respond to it more effectively. Of course, this doesn't replace the basics, hydration, balanced diet, individualized treatment plans, but it does suggest a future where kidney stone prevention might include metabolic and cellular resilience as part of the equation, with molecular hydrogen as one possible tool. Imagine a world where after your first stone, your doctor not only talks about fluids and oxalate, but also runs an oxidative stress panel, where prevention means optimizing internal balance, not just restricting risk factors, where the kidneys are supported as adaptive organs, not just passive filters. That world isn't here yet, but the research carefully, incrementally, and grounded in real biology is starting to point us in that direction. Kidney stones hurt, but they're also trying to tell us something about how the body handles stress, inflammation, and imbalance over time. If molecular hydrogen can play even a small role in helping the kidney weather the storm, that's worth exploring, not with hype, but with curiosity, caution, and good science. That's it for today's episode. You can find any studies referenced in this podcast on hydrogenstudies.com. Join us next time for more on how molecular hydrogen is changing the game. Until then, stay healthy, stay curious, and catch you next time.